Thank you. So good afternoon, everyone. I believe a lot of you are probably more familiar with my colleague, Jake from State Farm. But okay, so my name is Priya Sundararaman, as I was already introduced. I'm a principal data scientist with State Farm. I've been with State Farm for about 3 years now. The topic of discussion today is deep learning techniques for identifying distracted driving behavior. So why distracted driving? Distracted driving is very slowly becoming the new drunk driving issue here. And coincidentally, this month, April, is the Distracted Driving Awareness Month. I'm not sure how many of you were aware of that, but it's the Distracted Driving Awareness Month. So obviously, it's a problem that's important enough for the National Safety Council to dedicate an entire month for the awareness and campaigns and things like that. So let's talk a little bit about what can we do about it. I'm trying to see if this works. Okay. A little bit into the numbers. Devil is in the details. So let's look at what statistics say. Both the infographics, I believe, were pulled from the NHTSA website. The one on top actually signifies the magnitude of the problem. So approximately 3,500 deaths and 390,000 injuries just because of distracted driving alone. And these numbers are from 2015, which is a couple of years before. So most likely these numbers have gone up by now, so this must be a conservative estimate. And the other infographic actually talks about what we mean when we say distracted driving. The immediate thought that comes to our head is texting. So it's not just texting and driving. There are other behaviors. It could be cognitive, it could be manual, it could be other visual distractions that we face when we are driving. And we will jump into these in the next couple of slides about how we define what is distracted driving. Those would be the targets that we would use for our classification. Okay, and the other thing I wanted to point out too is as an insurance company, why would State Farm be interested in this? The number one mission for State Farm is to help people live their everyday life comfortably without any risks. And so obviously, by identifying distracted driving, we are making our drivers safe, and hence it complies with our goal. So that's the problem that we are defining right here. Okay, solution. So the first step to a good solution is probably defining the problem. So we just looked at the problem as to why it is relevant today and why it is important, and then how it ties back to insurance or insurance companies or anybody in general. Why is it important? So now that we know it's an important problem, what kind of solutions can we come up with to tackle that? One possible solution, there can be many solutions to tackle this. One possible solution is, can we identify and classify distracted driving behavior using deep learning and computer vision techniques? And this is a question, and we are going to look at the research done to see if the question gets answered or not. So most of us, and me included, most of us believe that we can multitask seamlessly. Raise your hand if you have not been on the phone or done something else, eat or drink something while you're driving your car. So all of us are guilty of that. So we couldn't be more wrong about that, unfortunately. Again, I'm going to quote NHTSA on a parallelism which I thought was quite interesting. And that is, every time we look at our phone, it's equivalent to removing our eyes from the road for about 5 seconds. Anybody with a conscious mind would not really do that, but we are not aware of it half the time. So if we knew how to detect distracted driving actions and do something about it, maybe alert the driver, we could save more lives. Maybe the statistics that you saw in the previous screen would be much lower. So that's what we're going to try and see if we can solve today. The box on the bottom basically talks about a broad level of distracted driving activity that we may be trying to detect using machine learning or deep learning techniques. One is texting or calling, which we are all very aware of. The other is adjusting radio, something that's more manual, which involves you to be disengaged on the road and be more interested in what's playing on the radio, something like that, where it distracts you cognitively as well as manually. And then eating or drinking something, where again, you have your hands off the wheel and things like that. And then reaching for something in the back, looking behind, talking to somebody in the back seat, actions like that. And this, there could be other actions as well. Grooming, we all know, is a big culprit, and things like that. And then we narrowed down to a set of distracted driving actions that we would use for our research, which again, I will talk about in more detail in the next slide. So our hypothesis, very simple. We want to have a simple process which can be easily measurable, something that we can use to detect distracted driving and do something about it. So 3 main steps. How do we identify the gestures? How do we know what the driver is doing in the car? How do we record that? Second, what do we do with that data? Build a deep learning model, use computer vision. What do we do with that? And then the third thing, ultimately with the analysis, what are we trying to use the analysis for? Alerting the driver real time, giving them a driving log when they're done with the trip. What do we really want to do with that? So if we can do these 3, then we have a possible solution. So another parallelism that I wanted to bring up here was we all know about autonomous cars, self-driving cars. And this is kind of similar, but different in a way. Similar in the sense using machine learning, using deep learning, artificial intelligence to identify the surroundings of the car versus what the car itself is doing, constantly grading that and making sure the car can drive by itself. And this is the other side of the coin, where we're trying to use the same techniques. We're using artificial intelligence, deep learning, but it's inside the car. What's happening inside the car? And can we do that? That's the question we're trying to answer, and this is the hypothesis. And so what we decided was, in order to do an analysis, you need data. How do you collect data? That's going to be pretty hard if you need data for distracted driving behavior. It would actually mean having someone drive on the road and perform distracted driving actions and then record those actions and use that as the data for training a model. But that would be a really, really dangerous thing to do, and we could not do that. And so the main criteria for us for designing this experiment was safety. How do we ensure that our drivers are safe while we record this? And obviously, we needed volunteers to collect the data. So this was a well-planned experiment so that we could not only collect the data, but label it accurately. Half the time, we have data, but it's messy or it's not correctly labeled, and so your analysis is just as good as the data that you have. So we didn't want to run into that issue. We wanted to do it right from the beginning. And so this is in our home office, which is in Illinois, Bloomington. We got about 82 volunteers who agreed to perform or generate data for this experiment. And what we did was we had the driver sit in a car, and we had a tow truck pull the car across a particular route. And then while the tow truck pulled the car, we had 2 cameras, and I'm going to talk about why 2. We had a 3D sensor, and we had a camera on the dashboard, and we had the drivers perform the distracted driving actions in a particular sequence. We'll say, okay, for the first X seconds, have both hands on the wheel, and then the next X seconds, have the phone, talk something on the phone with your right hand. And so we basically orchestrated what the drivers would actually do so that when we got the videos, ultimately, we would have accurately labeled data, which would be good for training the model. So that's what we did. And we had a police escort and stuff like that. It was all regulated, and so it was so there was no risk to the driver, essentially. And I spoke about 2 devices. One is a 3D sensor device that we used, and the other is 2D, any normal web camera, which would give us like a JPEG image, like a video. So that's what we used on the dashboard. The images that you see in the bottom basically kind of gives you an idea. I don't know how many of you have experience working with 3D sensor images, so I just had a sample out there. And that one is plotted using an open source tool called Mesh Lab, I believe. And so the one on the left is what you get from a 3D sensor. And what a 3D sensor does is it does not give you just the X, Y dimensions of the pixels. It gives you X, Y, and Z. And the Z denotes the depth of of the image at every single point. So if I was driving the car and if the sensor was here on the dashboard, it would have a depth associated with every single point on my hand. And the depth would vary because of the distance from the camera. And it essentially does that using some infrared rays, reflection from that, and then the time taken for it to come back and calculates distance based on that. So that was good. We wanted to know the additional information. Is it providing a lift? So we wanted to record both at the same time. And then, of course, we all are aware of what 2D images look like. So we got a video of the drivers go through the set of motions like I explained. And we got frames from that video. And these frames would be the basis for us to train and validate and test our model. So that was basically the experiment and the data, how we got the data. So I mentioned I'll be talking about the targets that we defined earlier. So we had about 72,000 images from the 3D sensor as well as the 2D web camera. And the classification targets that we defined was 8 targets. I know you see 6 here, but the left and right were 2 different targets. I just clubbed them together. So you have the safe driving, and then you have the texting, the phone, adjusting the radio, eating or drinking, reaching for the back seat. We had a couple more. We had talking to somebody behind, and we had grooming, which we kind of removed later for a couple of reasons. Because grooming did not really make sense for men who were in the data set that we were recording. It made more sense for the women. And so we kind of thought, okay, we wanted a more representative, a more general model first before we jump into details like grooming. Similarly, looking back was very similar to reaching back, so we didn't use that for this first version of the model. So these were the 8 targets that we stuck with. I believe most of us in this crowd know or have modeled with image data in the past at some point. But I just thought this might be useful for somebody who's not played with image data before. So I'll make it really quick on this slide. It's just a comparison of machine learning to deep learning. So when you think of machine learning, you look at if you have unstructured data. You can't feed unstructured data like an image or audio or text directly into a model. You need to essentially pre-process it first to pull out the features that you need from that particular unstructured data. For example, for image, maybe you want to do some scale invariant transforms. Maybe you want to do some run some Sobel algorithms to get edges or something. You would have to manually create those features and then convert those in some kind of a matrix or an array of numbers and things like that before you can even feed it into a classic machine learning, random forest or some model like that. Similarly, with audio data, you may want to do some frequency-based features or something else doing with fluctuations or modifications in the spectrum of the audio signal. Or everybody knows about TF-IDF. We know about bag of words and things like that that we do on the text data. So you would have to manually decide what kind of features do I want on my data and then perform those pre-processing steps and then go into your handcrafted features and converting that into numbers and then feed it into a machine learning algorithm, whatever you want to use. The big difference with deep learning is that you don't do that. You don't do the feature engineering yourself. The deep learning algorithm itself identifies what the features are, and it iterates to the best features that are useful for this particular classification. So that's the big difference when you move from machine learning to deep learning. And so with unstructured data, deep learning methods have known to work very well, at least from academia, the research that's done, and people who have used it before. Deep learning is known to perform better because the machine can optimize the features much better than what we are able to do from a human being standpoint. And so that kind of works really well in the past, or we've seen better performances. On the right-hand side, you can see a very basic diagram. I know all of us know deep learning, but just for the benefit of anybody who does not, deep learning, what it does is, that's an example of images. When you feed images into a deep learning neural network, the first few layers in the top, you would see extracts the basic features, base level of features. For example, if it's an image, it would look at the corners, edges, and things like that. And as you go deeper, you start identifying parts of the image, so it gets more finer. And then ultimately, very close to the last few layers, the fully connected layers, you're able to identify what that particular object or image is about. So that's a very simplistic deep learning neural network, what that looks like. Obviously, we have a lot of variations to this. We have a lot of well-known architectures. We have VGG, we have the Google's Inception model, and then ResNets, and all of these have some kind of a variation. It caters to a particular feature. It's either making the performance better, or it's taking less space, and it can scale better and things like that. So depending on what the use is for your particular deep learning model, you may use one of those existing architectures as well. So I'll talk about that in just a little bit after talking about preprocessing. Okay, so I just mentioned that you don't need preprocessing. It automatically identifies features. That's just what I said with deep learning. So we had to do some because of the 3D data that we were dealing with. For the 2D data, it wasn't much. We just reduced the size of the images. It was like a 640 by 480 or something like that, and we had to just make it smaller so our network would be a more manageable size. It would be faster to run through it, and so we just had to reduce the size, and it wasn't a big deal with the 2D data. With the 3D data, so there were a couple of things that we had to do even before feeding it into a deep learning neural network. So the first thing, 3D data is typically, it is represented in a polygon format. Polygon format has this X, Y, Z coordinates that I mentioned, but it also has the associated metadata and all those things within the file. So we had to somehow convert that and then into a NumPy format. That's the first step. The next thing was we had to normalize. What I meant by normalization or standardization, I don't know what's the right word for that, but what happens with 3D data is we do not have the same number of points with every single frame in a video. For example, if I was driving the car, if I take my hands off, the next frame would have significantly low number of points. So the number of points would vary from frame to frame in the video. And so that's a problem because you cannot feed a varying number of frames into a neural network. And so you need a standard set of points. And then you can't even just trim out the last few because they are not ordered in the same way, like left to right, top to bottom, X, Y coordinates, excuse me. They are not ordered in the same way. And so we had to figure out which of those points do you remove? How do you standardize that to a standard set of points before you get to feeding it into the neural network? So I'm just going to jump into the next slide. I'll go back to the previous one, but this essentially talks about what we did to standardize the points. So we took all the frames that you could see in the 3D videos, and we identified the minimum and maximum XY points on all of those frames. And once we identified those, this is on the training data set, we were able to come up with a grid with a minimum XY, maximum XY, build a grid. And then the grid had an interval of some threshold. We set up a threshold of 10 or 5 or something, I don't remember. But then we had an interval, so this would create a grid. That is the first step. The next step was to map every single frame from the video to this grid. So what we did for that was we used a KD tree algorithm from SciPy. And what that would do is look at every XY point on the grid and identify the nearest XY point on my frame with the XYZ values, and then get the Z value from there, from the nearest XY point to the grid. So that way, we have a standard grid with XY and Z values, and it's close or pretty approximate to the original video frame that we had. So that's how we circumvented that problem. Of course, we ran into issues. It was taking a long time, and we had to run some multiprocessing pooling methods and running it on multiple threads and CPUs at the same time to have it finish in a few hours. But then we got through that bump. So that was the pre-processing that we had to perform before we got the XYZ points and ready for the model. Yeah, with that done, the only other thing left was to split into training and test data sets. We did not have, I mentioned we had 72,000 images. Seems like a lot, but when you are training, if you're not doing transfer learning and if you're doing training a neural network from scratch, it's not too much. So what we did was we had 82 drivers, like I mentioned. We used 7 of those for the test case. and then 5 of those for validation, and the remaining 60, which is about like 50,000 images, was what we used for training. Okay, so I mentioned a few architectures that people could use. We used something close to the VGG16 architecture, not the same one for sure. We scaled it down drastically, but it was similar from an architectural standpoint to the VGG16 architecture. I'm going to just talk through some of the hyperparameters and things that we used. We used Keras with, we tried Theano and TensorFlow in the back end. The difference in the speed of both when we ran on a GPU system was not quite significant. So the results that you see here would be from the Theano run today. So what we did was we had 4 convolutional layers. So it was 2 convolutional layers and then a pooling layer and then another 2 convolutional layers, pooling layers, and then we had 2 fully connected layers in the end before the output. So that was the architecture overall. We had the ReLU activation on the convolutional layers. And on the final one, we had softmax because we are looking at a multi-class classification with 8 targets. So we had softmax on the last layer. We also had to do batch normalization. And what I mean by that is the image that we fed into the neural network, it was normalized. But then as you go through the convolutional layers, the distribution could get a little skewed because some of the feature maps, the range of values that you see, it could be like 0 to 1 or 0 to 999 as it goes through the convolutions and the computations. And so we had to normalize it after the convolutional layers, and that helped it converge faster and improve the performance of the neural network itself. And then the loss was log loss, categorical cross entropy that we used to determine if the network was converging and how well it was converging. And then we used stochastic gradient descent to go back and fix the weights of the neural network as we went through the cycles. We also broke it down into mini batches of 1,000 images at a time, and we had those go through the epochs and then train that way. It kind of worked better as compared to feeding in more images, especially when a lot of the images, if you think about it, we had videos, and we broke them down into frames per second, like 4 frames or something like that per second. So you would have a lot of images that are doing a similar action. Like if it's a normal driving, the difference between the normal driving in the first frame versus the second frame would be kind of minimal, but it would be very similar. So it kind of helped us when we shuffled the images and then we did the batch processing. That kind of helped us with the training as well. We used a GPU for training. That drastically reduced the time. Initially, when we ran it on a CPU server, it would take us a day, and then it came down to less than an hour when we used the GPU server. I think that was all about the, and of course, if you have any questions on the hyperparameter tuning, I can talk about that later. Okay, a little bit on the results. The results look fantastic. And again, I'll tell you my hypothesis in the end about what I take away from this analysis. So if you look at the confusion matrix, it did pretty well on most of the categories, except maybe the left-hand calling, maybe a little bit on the eating and drinking category, if you look at some of the F-scores on that. But overall, it looked like it was able to predict pretty well. And then the graph shows the validation and training loss. It's kind of tracking it. And this is not transfer learning. We're training this from scratch. So, and again, this is after multiple tries of, okay, what kind of, how many convolutional layers do I need? How many fully connected layers do I need? After doing a lot of permutations and combinations on that, this is what we landed, which worked best for the data that we had. So this is the ultimate result, and this is for the 2D data. We had something similar for the 3D data as well. For the 3D, the architecture was slightly different. We had, I forgot to mention one thing, we had the dropout neurons set after the convolution, after the pooling layer. And so the dropout percentage, we kind of had to change that a little bit for the 3D. architecture. We had more convolutional layers on the 3D architectures. There were some changes, but overall, it was a VGG-like architecture. So I didn't want to just repeat that, so just shared one of that with you guys. Overall, high level, if you look at the ensemble, so let me talk about the ensemble. So we ran this on the 2D images and the 3D images. Initially, it was just a curiosity thing. We just wanted to compare, oh, does 3D perform better than 2D? And in fact, we started out on the 3D data using a random forest model just to have a baseline. Okay, what is my baseline? It wasn't too bad because the 3D data itself had additional information about the actions, like the depth was a big predictor for us. And so the random forest model was okay. So our main curiosity was, okay, how would a CNN perform? And it was a big difference between the CNN and the random forest on the 3D data. So a lot of this we started out just out of curiosity and research and things like that. So if you look at the overall accuracies, the 2D data, the accuracy is like 86%, and the 3D data accuracy is something close to 93%. Obviously, you expect that. It has more valuable information, so you expect the model to perform better or be more predictive. And so what we did is, what would happen if I combine the two? If I took the 2D data and the 3D predictions, and if I combined the two and ensembled it, what would happen? And so obviously the ensemble was much high accuracy. 96% or close to 97% is what we got on the ensemble model. So how did we ensemble it? So you know some of the initial steps where you get the videos and break it into frames and things like that. What we did was, when we got the videos, we kind of associated the timestamps with the frames on the videos, and then we broke them into 5-second chunks. And every 5-second chunk, the frames that existed in the 5-second chunk, we passed those frames into both the models, the 3D model and the 2D model. And then overall, what we did was we aggregated what was the maximum voting, what was the prediction that was predominant in that 5-second chunk across both the models. And that is what we said was the prediction that the person was doing. Because it didn't make sense to evaluate every frame, because that would be like a really fraction of a second. So we went through a 5-second chunk and saying, okay, in the 5 seconds, maybe 50 frames, what were you doing? And then we just aggregated the maximum as the action that the driver was performing. And then we ran that through the entire video, and then we had the log like what you see, saying, okay, this is Priya at 10:01, you were driving at 10:01 and 30 seconds, what were you doing? And a log or something like that was what was spit out from the model. So that's what we actually, that was the output of our model. But then this is something that was one of the suggestions that we had for, how would we use something like this for real-time monitoring or real-time alerting a driver. So what you would do is basically take the 5-second chunk and then send the action that they were performing to a cell phone or something that the driver had, and not necessarily make it visual because then we are promoting distracted driving again, but make it more audio or something like a beep or whatever. But then that could be one of the solutions that could be derived from something like this. So that was how the ensemble worked. And now I want to talk a little bit about the architecture that we used and what I think about this model and how it can be improved. This was not something that was built for production-ready use or for deploying in people's cars and drivers and track and send them logs right away. This was more like a proof of concept. Can I do this? Can I use this technique to solve this problem? And so the architecture is a little kludgy, I would say, but this is what we did initially. So from the driver, you would have the sensor and the camera, and then you connect the sensor and camera to a laptop in the car, actually. Honestly, I'm not even kidding. And then take that from the laptop and then transfer those images into a GPU server, have the model predict on those images, and then send the prediction into create a log or something of that sort, and then send that back to the driver. So this was the architecture that we worked with, but then we weren't focused on scaling it or making it production ready or the architecture. We were more focused on the technique that we were using to solve the prediction problem in the first place. So improving for the future. This is the final slide. So I've mentioned a more robust model. So this model, you saw the performance was great, 96.9%. That's pretty awesome. So what do I mean by a more robust model? If you go back to how we collected the data, this is one or a couple of cars that we used, which was towed by this towing truck. So obviously, all of our images would have a similar background, not only in terms of the route that the car took, what you can see through the window, the driver's seat window, but also in terms of the internals of the car itself. So the images are pretty standard if you think about it, from a training standpoint. It's a very controlled environment that we collected the data in. And so that's number one. And number two, we had the driver perform actions which were very predictable, I would say. We had the driver say, okay, use your right hand and then call. What if somebody had the phone on the steering wheel while they were driving and they were texting? Oh, and we know many people do that. And so those conditions were not inputs to the model at all. So we were going through a set of actions which made most sense to us, for example. And similarly, when somebody's grooming or whatever, when they were reaching back, we had people do that, but then, maybe they don't look all the way back, they only look slightly or whatever. So we had people perform these actions in the most obvious way, but what if real time people are not behaving in the most obvious way? And so in terms of data collection itself, it was a very controlled environment where we did the research. So how do we make this more robust? Number one, we collect data in a more diverse environment. That's number one. We make sure that we go through these actions where there are multiple versions of texting or calling or any of these actions. That's number one. And then see how the model performs. And maybe you have to tweak the model. Maybe you have to add more layers, make it deeper in order to identify those things. There could be other techniques applied. For example, we ran it on the entire image. We could take pre-process the image in such a way that you take like a subset of the image, like the face and just the hands, and then just use those to improve your neural network. So things like that, those could be suggestions to make the model identify these actions irrespective of how it was recorded, what the background was, and things like that. So that's one. And then obviously we could add more actions too. Like grooming was one which we dropped out, but we could add more actions that could make the model more robust. So that's one of my first suggestions. Second suggestion is the architecture. So we had, I shared the current Kluge architecture, which worked, which served the purpose, and that's fine. But then going forward, it should be something, or at least we envision it, something that can actually run on the device in the car, maybe using some kind of a processing chip within the device. But then when the driver's driving, it records a video and then does all the pre-processing, runs the model, gets the output. All that has to happen within the processing in the processor or chip or something within the device, and then send that feedback right to the driver on his cell phone as and when they are driving. And so that would be the ideal case for a real-time monitoring. So obviously improving on the architecture, scaling on that would be the next step on this. And then the last point here that I have is combining this with other driving behavior models, and that is to make this a more comprehensive driver safety application. If we wanted to do that, we might have to go beyond just the actions that we looked at, cognitive, manual, visual. We might have to look at finer features like, is the driver sleepy? They're driving, so maybe just honing into the eyes, or identifying, looking at some features maybe on the face, like yawning and stuff like that, or maybe there are something else we can do with drunk driving based on the eye movements and things like that. So how do we make this more comprehensive? Maybe integrating it with models like that might make it a more comprehensive driver safety application or model. And so that, I believe that's